Alright, now we're going to take a look at another set of problems which we call classification problems. Yeah? What is classification problem? Well, you get some input data and you predict what class this data is belonging to. In the simplest form, you have a binary classification problem. You could say, based on a brain scan, you could decide the person has tumor or no tumor. This is a classification problem. This red line here is the decision boundary, and you can see that the plus class equals y equals to 1 is on one side, and y equals to 0 is on the other side. So 1 is tumor, 0 is not a tumor. Now there's not only binary classification, there is also multi-class classification. Remember when I discussed about the history, there was AlexNet, and one did not win, but was number 5 in the ImageNet competition. So there you have 1.4 million high-resolution pictures, and you need to distribute them in 1,000 classes. So that we call a multi-class classification problem. You'll often also hear softmax. A term that is very frequently used in machine learning. So here you see that you have another type of decision boundary where you split the pluses from the minuses from the triangles. Okay? So if you have k classes, y is an element of this group. Now we drawn here linear boundaries, but a decision boundary can also be non-linear. Here you have y is 0 outside of the circle, and y is 1 inside of the circle. Okay? So now let's come back here, and we have an example here to make you understand how classification works. So we have again input data, very similar to regression. We have one feature, the xi, the feature of weight in kilograms. And we have then the label, the outcome, which we call yi, and the label is 0 when the person is not obese given its weight, and is 1 when the person is obese given its weight. Here you see again we have 6 training samples, so m equals 6. So the computer now will learn the probability distribution of having a tumor given its weight. I don't want to go in detail at this point right now. We'll talk more about this when we discuss classification algorithms. But here again, it's a hypothesis working on the x of I gives you a predicted value of y. But you see that basically you have the weight is the x-axis. Let me put it this way here. You have the weight on the x-axis. Actually, I've written it here. So the x-axis is weight in kilograms. The y-axis is a 0 or a 1. That means obese or not obese. So let me take this one away, not to confuse you. So how can we go from a linear score to a probability between 0 and 1? Well, this is also what machine learning is doing. In machine learning, we learn transformations so that we get the information that we want. For example, in this case, we can work with a function like this. And we will also discuss this later. But this perfectly matches the linear score to a number between 0 and 1. And this is 0.5. So the people here will be classified as not obese, because they're gonna fall between 0 and 0.5, and the people here will be obese, because they're gonna be between 0.5 and 1. So whatever you score, you score in the middle. For example, you will have a score 0.74. Well, if the score is 0.74, the person will be classified as obese. Okay, now how do we measure the performance of a classifier? Well, it's quite obvious, you might think. It's the number of points classified correctly. But this gives us a problem. For example, we could think of a classification problem where you will try to detect when a credit card transaction is fraudulent or not. Yeah? The problem with this is a very imbalanced problem, because 99.3% of the transactions are not fraud. And we try to find the 0.7% that are fraud. Yeah? Now, if you put that input data into your computer and you learn the model, the computer is gonna outsmart you, and basically the computer will decide not fraud in all cases. Right? So the computer will not even look, say not fraud, and suddenly you have an accuracy of 99.3%. And this is of course not what we want. We want to detect the 0.7% that are fraudulent. Yeah? So we'll look at these as well a little bit more in detail.